From sine waves to phasors, a complete journey. Let's begin by understanding the building block of our discussion, the sine wave. Here we see a simple sine wave, described by the equation y equals sine of x. It has two fundamental properties. First is its amplitude, which is the maximum height or peak value of the wave. For this basic wave, the amplitude is 1. Second is its period, which represents one complete cycle of the wave. Let's look closer at amplitude. As we define it, it's the maximum height of the wave. If we plot sine waves with different amplitudes, you can see how the peak height changes. A smaller amplitude means a shorter wave, while a larger amplitude results in a taller wave, signifying more intensity. Next, let's explore phase. Phase simply represents the horizontal shift of the wave. If we plot a standard sine wave and another one with a phase shift, denoted by the Greek letter phi, you can see it's the same wave, just shifted left or right. This phi tells us the wave's starting point in its cycle. Now, let's move to waves in time. In the real world, like in electronics and communications, waves aren't static. They oscillate and travel through time. This animation shows a wave moving, which we can describe with an equation that includes a time variable, t. The general form for a real-world sinusoidal field is given by this expression. Here, a is the amplitude, omega is the angular frequency telling us how fast the wave oscillates, and phi is the phase. This brings us to a problem. Working with these time-varying equations can be very complicated, especially when we need to perform calculus, like taking derivatives. For example, taking the time derivative of our cosine function changes it into a sine function and introduces a negative sign. As equations get more complex, this becomes messy very quickly. So, how do we simplify this? We turn to the magic of complex numbers. Our secret weapon is a beautiful mathematical identity known as Euler's formula. It states that e to the power of j theta equals cosine theta plus j sin theta, where ej is the imaginary unit, the square root of -1. Euler's formula gives us a powerful way to visualize waves. We can represent a wave as a rotating vector in the complex plane. The projection of this vector onto the real axis gives us our cosine wave, and the projection onto the imaginary axis gives us our sine wave. Why is this so amazing? Because derivatives of exponentials are incredibly easy. The derivative of e to the j omega t is simply j omega times e to the j omega t. All we have to do is multiply by j omega. Compare this to the derivative of a cosine, which changes the function to a sine. The exponential form is much simpler to work with. This leads us to, what is a phasor? A phasor is a complex number that cleverly represents the amplitude and phase of a sinusoid, while hiding the time dependence. We go from the time domain with its complicated cosine function to the Phasor domain, represented by a simple complex exponential. We can do this because in many systems, all waves oscillate at the same frequency, omega. So we can just factor out the time-dependent part to the j omega t and work with the much simpler phasors. Let's walk through the conversion. We start with our time-varying field. Using Euler's formula, we know that the cosine term is just the real part of a complex exponential. We can then rewrite the field expression like this, separating the time-dependent part from the rest. The phasor is the part that contains only the spatial and phase information. To get back to the time domain, multiply by e to the j omega t and take the real part. So what does this e to the j omega t factor represent? As we saw from Euler's formula, it's a vector of length 1 that rotates in the complex plane. As time increases, it spins counterclockwise at a constant angular frequency, omega. And why do we factor it out? Because in a linear system, all the electric and magnetic fields will be oscillating at the same frequency. This means they all share the same e to the j omega t factor. It's just like in basic algebra, where you can factor out a common x from an expression. Here we factor out the common time term. So this is the complete picture. The time domain representation includes the messy cosine and time dependence. The phasor domain simplifies this down to just the amplitude and phase. The time factor is not gone. It's just implicit or hidden to make our lives easier. Now for where the magic really happens. With phasors, time derivatives become simple multiplication. If we take the time derivative of the full time domain expression, we see that the derivative only acts on the e to the j omega t term, which brings down a factor of j omega. The result is profound. The time derivative operator is simply replaced by multiplication by j omega. This is the golden rule of phasors. When working in the phasor domain, every time derivative is simply replaced with j omega. This turns calculus into algebra. Let's apply this to Maxwell's equations. Here they are in their time domain form, with those problematic time derivatives. Let's convert them. We replace script letters with phasor letters, replace the time derivative with j omega, and use the constitutive relations b equals muh and d equals epsilon e. Let's try an example with Faraday's law. We start with the time domain equation. First, we replace the script letters with phasor notation. Next, we replace the time derivative with j omega. Finally, we use the relation b equals muh, and there it is, the clean, simple phasor form of Faraday's law. Now let's do the same for Ampere's law. Here is the time domain version. Applying our rules, it transforms directly into the phasor form. The time derivative becomes j omega d. Using the relation d equals epsilon e, we get the final phasor form of Ampere's law. And there it is, the clean, simple phasor form. And now, the complete set of Maxwell's equations in phasor form. Notice how clean they are. There are no time derivatives. All the complex time-dependent behavior is now captured by simple algebraic multiplication with j omega. So why are phasors so powerful? They simplify differential equations into algebraic ones. This makes analyzing circuits and electromagnetic waves vastly easier, and the notation is much more compact. However, there is an important note. This method only works under a few key assumptions. All quantities must oscillate at the same frequency, the system must be in a steady state, and the system must be linear. So here's the visual summary. We move from the complicated time domain to the simple phasor domain by removing the implicit time factor, turning hard problems into easy ones.